Welcome back. We just got done talking about HPLC, which is this part of the LCMS system. And this is a Q Exsactive. We've got two of these in our lab, and we also have a Fusion Lumos. But there are many, many other types of mass spectrometer, and I'm going to cover very basic principles of that apply to all mass spectrometers. But ultimately, most of what I'm going to talk about applies specifically to this particular mass spectrometer here. So what is mass spec? Essentially, you can think of a mass spectrometer as a device that measures acceleration of ions, because that's kind of all it does. So I said in the last video that what we're really interested in the way we use the mass spectrometers is comparing, identifying whatever molecules are in a particular biological sample and then comparing what changes between different conditions. That's usually what we're doing. But really what we're measuring is just acceleration. And then it comes from these two basic formulae, F equals QE, which is down here, right? So if you've got a particle that is, say, positively charged and it's in an electric field, which is between these two electrodes, it will travel in that field. Why does it travel? Because it experiences a force, and that force is equal to the charge on the particle multiplied by the field strength. So it's quite important to recognize that the charge on the particle plays a part in the force that the particle experiences. So if this is an ion, it could have an extra proton compared with a molecule, and so it has a charge state of +1, or maybe it's got 2 extra protons, then it's got a charge state of +2. The difference is that with +2, it'll experience twice the force, and that means it'll accelerate at twice the rate, which comes from this second equation, F equals ma. So a thing will, let's rearrange it, right? So what it really means is F over m equals a. So a thing will accelerate when you put a force on it in inverse proportion to its mass. And the force that you're putting on it is QE. So we can replace that with QE. And so we have this charge over mass multiplied by some constant is equal to acceleration. I'm just going to remove that and say that that's proportional. And then if you flip it on its head, you get something over here. So mass divided by charge is equal to the field strength divided by the acceleration. I'm just going to get rid of all this stuff. So what we're really saying is that mass over charge, and I'm going to call it Z because that's what we call it. It's a slightly different thing that we're saying, really, but mass over charge is proportional to 1 over acceleration. So if we can measure the acceleration of a charged molecule, an ion, in an electric field, then we can say what its mass to charge ratio is.
This ratio in, I guess, atomic mass units over charges, protons. So it's measuring the charge.
In mass spectrometry is ionizing the sample. And this happens in some kind of a needle at the front of the instrument. Well, it's not always a needle, but we're going to concentrate on that now. I'm not going to talk about the other modes of ionization. So in our case, it's a needle, or it's the packed emitter on the nanoscale. And a voltage is applied to the system is a couple of thousand volts. And this forces charge into the solution. And then at the end of the needle, the stuff is sprayed out. And there's some charge in there. And what happens next as these droplets are sprayed out of the needle, and then they start drying down. On the normal scale HPLC, we'll use dry nitrogen, spray it at the droplets that come out of the needle to try and get rid of the solvents. On the nano scale, we don't need that. They dry themselves. But in either case, the droplets get smaller and smaller, and the charges in the droplet are trying to get away from each other all the time, because like charges repel each other. And eventually the droplet gets so small that the electrostatic repulsion overcomes the surface tension of the droplet, and the whole thing explodes, and the charges are then left stuck to your molecules of interest, hopefully. So then at this stage, we have something that we can put into the front of the mass spectrometer. We've got ions, and they can go in here. In here, there's a tiny little hole, and stuff goes in. Inside is a vacuum, and so it sucks things in. It sucks in the ions that you've ionized. It sucks in molecules that haven't been ionized. It sucks in air from the room. And I've put the schematic down the bottom left there. This is the area we're talking about on the schematic. When the engineer visits, we take the covers off, and I take loads of photos to show you guys what it looks like inside. So we're just going to have a quick look at that now. So this is where the ions come in, the front of the instrument. This is with the cover off, and you can see stuff behind there. So this is the front of the instrument. This is an ion transfer tube that carries the ions from the outside to the inside, where it's a vacuum on the inside. And because it's a vacuum, the ions try and spread out as they come in, along with the gas and everything else that comes in there. So this thing here, which has several names, an API stack, a Shrig, an S-lens, and I've heard them used interchangeably, even though that they have very specific meanings. Whatever, it's some kind of an ion funnel is what it is. It takes these spreading out ions and focuses them into a beam, which can then be more easily manipulated by electric fields further into the mass spectrometer. This is now a view down the top of the mass spectrometer, and if you look at the schematic, this is the area we're talking about. Well, no, it's not actually, is it? This is the area we're talking about. So this little bit on the corner here is this bit here. And this is called a bent flatterpole on this instrument. On the Fusion Lumos, it's called an active beam guide. The point of it is, I guess there are 2 points. One is to control the form factor of the instrument. So if you can redirect the ions in a different direction, you can squeeze your components into a smaller bench space. But also anything that's not charged will now just hit the back wall, which means you're not filling any further into the instrument with stuff that you can't manipulate. I guess that's kind of important, because the next part is quite difficult to take out and clean. So the next part is quadrupole. And this has many functions in mass spectrometry, but in this instrument, it's very specifically a mass filter. And it means you can select a particular ion of interest to take further into the instrument. If you want to, you don't always have to. And this is a view from the front again. So we're now looking, if you imagine on the schematic, there's a pivot point here. And all of this part on the left, in reality, is the other way around. So in fact, well, this is the front of the mass spec on this side. This is the front of the mass spec on that side. So what we're actually looking down this way. So kind of in that way. So the ions come out of the quadrupole, whether they've been filtered or not, and they go into a component that's normally in this space here called a C-trap. And it's like a bucket. You have a continuous stream of ions coming in, you fill the bucket. When the bucket's full, you empty it into the mass analyzer. And the mass analyzer is back here. It's called an orbitrap. We'll come on to that. I don't know if you can maybe see there's a tiny little hole in the front there. That's where the ions go in. And then this thing on the left here is a fragmentation cell. And there are lots of types of fragmentation in mass spectrometry. The basic idea is you break your molecule up into smaller pieces that are characteristic of the structure of that molecule. And from the masses of those, it can help you to identify exactly what that molecule is. This particular fragmentation cell is called HCD, high collision energy dissociation. And That's the only mode that's available on this instrument. On our Fusion Lumos, we also have CID, collision-induced dissociation, and ETD, electron transfer dissociation. So this is the C-trap, and this is now viewed from the top. So the ions come in this direction. You fill up the bucket. When it's full, you eject them out here. Or if you want to fragment a selected ion, an ion that you've selected in the quadrupole, then you can pop it out the side there to the HDD cell, which looks like this. It's very rare that we get one of these out of the instrument. In fact, on this occasion, it was because one of the pumps, the vacuum pumps on the instrument, failed and sprayed the inside of the instrument with pump oil, and so everything had to come out and get cleaned. That's really the only time this part would come out, I think. And this is a vendor literal cutaway of an Orbitrap. So when they make these things, it's very, very difficult to machine, and so I guess a few of them fail to make any kind of QC. And then why not cut the front off and show people what they look like inside? Anyway, the inside of this, let's say we've got positive ions coming in. The inside is negative, the outside is positive, and it causes the ions to orbit around the inside, like this. Then what happens is, for a particular ion, it will form a band of ions of that particular mass-to-charge ratio. I guess that's what I mean. For a particular mass-to-charge ratio, a discrete band will form, and then that band oscillates up and down the axis of this device. And the acceleration, that is the rate that it oscillates, is proportional to charge over mass. And so from the frequency that you get from this thing going up and down, you can figure out what the mass-to-charge ratio is. And then, of course, you've got more than one of these in there. So you have lots of bands in there going up and down, and then you get some kind of crazy waveform that's read off the two halves of the outside shell, the voltage, as these bands, these charged bands, generate a voltage across the outside. And then somehow from this complex waveform, we need to get to a mass spectrum. So everything on this schematic occupies quite a small part of the instrument, really. It's kind of in a plane about the, like not a mathematical plane, but you know, about that height, I guess, about a hand's width, if you spread your fingers. So it all occupies that kind of space within the instrument, and there's loads of space in the instrument above and below that, filled with other things that are not directly mass spec things. They just set up the right environment. So this, for example, is a turbomolecular pump. On the floor underneath this bench, there's a coarse pump that generates a really strong vacuum, probably better than any vacuum cleaner can do. Well, certainly better, really. But this thing then takes individual molecules and pings them out of the internal space of the mass spec. So that there are no molecules in there that can interfere with your ions that you're trying to control. And at the top, there are lots of circuit boards. These are control boards or RF readout boards that are sending or receiving information to the various devices. And there's also a computer in here that then does some number crunching before communicating with the computer outside the mass spec, which is the one we interact with. So we'll leave it there for now, and I'll see you in the next video.